I haven't even started yet. You don't know what you're in for, right? Yeah, thanks for the introduction. A few words about myself. I'm an engineer turned product manager working at Confluent, which is the company founded by the creators of Apache Kafka. We're based in Palo Alto on the US West Coast. And as I said, I'm now doing product management work, which is a bit different from what I did before. I'm a contributor to Apache Kafka, obviously. I'm also committed to projects like Apache Storm and a few others, but nowadays most of my work is really focused on Kafka. So before we start, let me ask a question though. Who of you here in the audience is familiar with Apache Kafka? Right? Well, let me take a picture. Okay, maybe there was one person that is not familiar with Apache Kafka. So for that person, let me briefly show this slide here. And what I want to show here is that Kafka started out as a messaging system, a PubSub system, whatever you want to call it, a few years ago. But nowadays, it's like a full-fledged stream platform, which you can also use to process the data in Kafka, for example, or integrate Kafka with technologies such as Hadoop, Cassandra, Mongo, and so on. So in this talk, I will focus on the part that added stream processing capabilities to Apache Kafka, the so-called Kafka Streams API. So as a motivational example, imagine we were to build a hotel business. We would need to implement a few roles, such as a security guard, and on the technology side, we could do this with, let's say, a single application or microservice that runs on one machine. Of course, reality is a bit more complex, so eventually we'd need to add further roles like a receptionist, room service, and so on. Again, more applications running on, more of these machines. This is already complicated, but it gets even further complicated on the technology side as soon as we need to scale out. So if we reach the point where one security guard is not enough, but we need a team of security guards, suddenly we need to run distributed applications across many machines, VMs, or containers. And at that point, it becomes typically very challenging for us, because then you're solving a distributed systems problem. And what we realized when we set out to design the Kafka Streams API for Apache Kafka was that we wanted to give something to developers that is part of the solution and not part of the problem. Because oftentimes it's a bit like yak shaving. You have your actual problem, and you start digging into these technologies, and it gets even more complicated the more you add to your portfolio of technologies. And I think a key part that we realized is that as app developers, we want to build applications. We don't want to build infrastructure or clusters. So we want our applications still to be a bit like these new technologies. We want them to be elastic, scalable, fault-tolerant, and a few more of these things. But at the same time, we wanted to question the commonly held belief, do we need separate shared processing clusters? Do we need separate shared databases if we want to do stateful processing on streams in Kafka? Do we need something like Redis or Cassandra just in order to do some counting, for example? So essentially what we want to do is something like this analogy. We want to enjoy the taste of beer, but we don't want to have the alcohol because we want to still drive home safely. And this is what led to the creation of the Kafka Streams API, and I will talk a little bit about the design choices that we did, the things that you can do with it, and so on. But the point here is that it is a tool so that you can build real-time applications that power your company's core business. If this thing isn't working, your company isn't working. And that meant, for example, that we built fault tolerance built in. It's not something that you need to enable in an obscure way. You explicitly need to disable it to get rid of it. Same for elasticity and so on. So we'll talk about that in a second. So you might be familiar with this concept of enrich my library, say if you're using Scala. And we're turning this upside down. We're giving you a library with the Kafka Streams API that enriches your applications. And what does that mean? It means you get features such as a cluster to go. I have an example in the next slide. A kind of database to go. You can run it everywhere. You can use it for very small use cases all the way to very large use case and smoothly go in between those. You get exactly once processing, even under failure. You can do event time processing, joins, aggregations, and so on, and a whole lot of more. So as an example, here's an application that uses the Kafka Streams API, and I just want to highlight, this is an application that does not run in the Kafka servers. It doesn't run in the Kafka process, but at the perimeter of it, in a VM, a container, or something like that. And if we want to scale out this application, we just spawn additional instances of the application. So I'll talk about that later on. But the point here is that this should be super easy. You shouldn't install Yarn just to run it on 2 machines, for example. So, motivating example here. Imagine you were tasked to create a real-time analytics dashboard like this one. My common use case would be, cybersecurity. You want to monitor whether any of your services is currently under attack by some adversary. How would you implement this use case? So typically what people have done, and I've done that in the past myself, you would collect data in real time in order to do these, analytics and so on. Then you would stand up a separate processing cluster, like Spark or Storm. Then you would submit a job to that cluster, and some of the cluster would write the results back to a database. And then you would have a front-end application that would query the database in order to show some results, like that roadmap. Now, what's the problem with that approach? One problem is, and I think this is one of the key problems that are not necessarily technical problems, but people problems. Here, what you can see is like the parts in blue. This is your application. It's spread all over the place. It's spread across systems, and typically it's spread across organizational boundaries. Like there is a cluster team that runs the cluster, a database team that runs the database, and then you are the lonely soul that tries to stitch everything together just in order to make this simple dashboard. So with Kafka Streams, you can collapse all of that into a single application that, if you want to, you can Dockerize and then deploy in Kubernetes. You can use it locally on your laptop in order to test it and so on. I have a few more examples like that. So one point here is that you can simplify your architecture a lot, but it also has radical implications how you actually develop, test, and deploy your applications in the first place. And that is what I want to focus on. But before I talk about that, how do you actually write an application in the Kafka Streams API? Well, you have 2 options. You have a DSL, which is what is shown on the left. This is more in a functional programming style way to write your application, a bit like Scala collections, for example. And then you have the processor API on the right, which is often used for more complex event processing. And the cool thing is, you can actually combine the 2. So you can have like the normal DSL flow on the left, but there are some certain steps in there that you need to optimize or do something very specific to your company, and you can just plug those in. So let's take the canonical word count example. Simple thing, we get inputs as text lines, and then we want to split the text lines into words and count how often we've seen a word. Now, how does that problem translate to how you would work with Kafka Streams? First, if you want to develop this application, you can do it on Linux, Mac, and Windows. I think Linux and Mac we can take for granted nowadays, but oftentimes people are stuck on Windows if they're working for a bank or an insurance company and these other tightly regulated industries. So you can use all of the common operating systems to do that. And here's the key code that you would write. First line is the one that reads from Kafka in a scalable way. The second statement is the actual word count, and the third line at the bottom is writing back to Kafka in a scalable way. This is not super interesting to talk about, but there is something that I want to highlight. Hard to see, but we have something called a K-stream and a K-table. What is that? So the thing that you realize when you start to get motivated to look into Kafka is that oftentimes you realize my business is actually real-time streams of information from customers, users, and so on. So like an ongoing conversation back and forth between you and your customer. So streams are everywhere. People here are familiar with Kafka, so I assume that you kind of understand the idea of streams of data and do this in real time. But the other thing that is important to understand is that tables and databases are everywhere too. There's a reason why we've been using databases for decades in order to build applications, products, and so on. So the key point here is to realize that in practice, you need both streams and tables all the time. Whatever you're doing, whether you're in logistics, in finance, in fraud, whatever, you need both streams and tables in order to solve your problem. So if you pick a stream processing technology, these should be first-class concepts in the API, for example. Even for word count, you need streams and tables. And something important to realize here is that there is a close relationship between the 2. If you look in the left column, there is a table that is undergoing mutations. If you capture those mutations into a stream, a changelog stream of that table, you can reconstruct that table elsewhere. And we're exploiting that functionality in numerous ways behind the scenes in Apache Kafka, and we also give you the option to exploit it in your own application logic. So for example, in Kafka Streams, you have a K-stream and a K-table. You have operations that take you back and forth between those 2. or those that retain the shape of it. Word count is a trivial example where you already need this. So for example, sometimes you have a stream and you want a table. Like you want to get customer information in real time and you want to build a continuously updating profile of every customer from a variety of sources. This is taking a stream and outputting a table. Sometimes you have a table and you want to get back a stream, for example, in order to make real-time alerts work. There are use cases where you have a stream and a table. You start with a table, get a changelog stream, transform that stream, and create a new table, like a new materialized view of the original table. Or you have a stream of data coming in, and you want to enrich this incoming stream with additional context information, like customer information about the customer that just paid something on, Apple in the Apple Store. Is this a fraudulent transaction or not? If this customer has never paid out of, I don't know, Australia, and so far only paid out of Europe, then most probably the Australian transaction is fraudulent. So going back to the word count example. Typically, other talks stop here, showing like these few lines and say that it's just one line or two lines. But let's zoom out of this a bit. What do we need to do in order to actually deploy this in production? In Kafka Streams, you only need a little bit to add. First, we need to configure, for example, where to find Kafka. And at the bottom, we just tell it to start doing the work. That's it. We have now an application that you can deploy locally on your laptop. And you can run at large scale to process millions of messages per second, literally like the code that I've just shown you. So that means whether you have a small use case, it's a good fit for Kafka and Kafka Streams. If you have a very large use case, it too is a very good fit for Kafka and Kafka Streams and everything in between. In the company I worked before, I would say that maybe 90% of the use cases were not large scale. Most of them are very small scale, but still important data, or maybe medium scale, but still important data. But we were kind of forced to use completely different technologies depending on whether we reached that threshold of having to push it across, let's say, from 1 to 2 machines, or at larger scale. And with Kafka Streams, you can use the same technology all the way through, from local prototyping, a manually installed proof of concept in production, all the way to large-scale automated deployments. But before we deploy to production, right, we want to test stuff. With Kafka Streams, what you're doing is you're deploying a normal Java, Scala, or Clojure application. So you can use any kind of unit testing tool and methodology that you like. You can also do integration testing with it and system testing as well. So since unit testing is a bit boring to talk about, let's talk about integration testing. So one thing you can do, for example, is if you have an application like WordCount that reads from Kafka, does stuff, writes back to Kafka, for your integration test, you can spin up in-memory processes of Kafka and services like Confluent Schema Registry if you're working with Avro, for example, and use schemas for your data, and any other thing that your company already has, and do your integration test against that. Yes, you can also Dockerize that and run it locally, run it on Jenkins, which also means that whatever your company is already using in order to do testing, continuous development, continuous integration, you can continue to use that. Just because you're working now on some medium to large scale data doesn't necessarily mean you have to completely change your tool chain and do something completely custom. Get approval for that from your InfoSec team, whatever. Now, assuming we tested everything, we want to deploy it. What would we need to deploy? Well, you can pick whatever you want. It's a normal Java application. Anything that can run or deploy a JVM application works, which means basically everything on the planet. So you can use stuff like Puppet, Ansible, you can use Vagrant, you can use cloud services, you can use Kubernetes, Mesos, even Yarn if you really want to. So all of that works. And why? Because there's nothing special to it. You're just deploying a normal application as it should be. You're not building infrastructure, you're building applications. So for example, with Docker, how would that work? Well, you have this code that I just showed you. You can compile it into a jar and create a Docker image for it. And then you just launch one or more containers, as many as you need, and you can do this during live operations without disrupting the data flow. I'll talk about that in a second. So it's super simple. It's so simple that people typically don't believe that it's actually working before they try it out. So, but let's stop talking about word count. Now, how does that work? So this is a 20-minute talk, so I can only give you a glimpse of it, like a trailer. But I try to at least give you some pointers to start with. So something super important for stream processing is fault tolerance, and particularly fault tolerance state, which I'll talk about in a second. Let's start with fault tolerance. Imagine you have an application that does stuff like word count. It remembers things that it has seen in the past, and then it needs to do something. If this machine fails, we want to make sure that we can migrate this work to a running machine. How do we do that? Well, the easy part is transferring the code logic, like your jar file. That is super easy. The tricky part typically is how to transfer the state in a way that you don't lose data. And what we're doing here behind the scenes is exploiting this relationship of a table is a stream, is a table, is a stream, and so on. So we're change logging the state of the application behind the scenes continuously into changelog streams or changelog topics in Kafka, and when we need it, we reconstruct it from there. And all this without data loss. So this is super cool for failure scenarios, but this is actually even cooler for normal operations. Imagine you have an application and you just run it on a single container, or a single VM, or a single bare metal machine. And this application does some stateful processing. Now you realize, oh, this one machine or this one container is not sufficient. I need more power to process the data. The only thing that you need to do is just spawn additional containers, spawn additional instances of your application. And Kafka Streams will automatically distribute, and like split and partition the state and make it available to the various instances, and they start collaborating on the work. This works during live operations, so you don't need to take down your core business just because you need to, add one more machine to the mix. I mentioned that at the very beginning, we really wanted to design something that is fault-tolerant out of the box, that is fitting an environment where you need to be running 24/7. So all of this, of course, works during live operations. And likewise, if you want to save money, you don't no longer need like 3 of these containers. You just stop some of them, and the remaining ones basically get all the data, all the state, and resume the work and continue working. So super elastic. Same for scalability. Imagine you're having a large incoming stream of data, and you need to do lookups against the database. Like in fraud detection is one example that I mentioned earlier. One of the drawbacks of such an architecture, I've done that in the past myself, is that for every incoming request, you have to hit a remote database across the network. So one of the downsides is you have a very high per record latency, and for some use case that is actually quite prohibitive. You really need to have like a few milliseconds and not like seconds of time. But also, you're kind of coupling the availability of your application with the availability of all these external systems. So what do you do if the database is down? Do you wait? Do you retry? Is that acceptable in your case? Are you violating an SLA if you wait for more than 5 seconds? So, and for that, what we allow you to do with Kafka Streams is, again, unifying the ideas of streams and databases and tables and kind of lift the database information into your application. So you're doing local lookups. You can exploit data locality, which is super fast, and also you're not coupling your application with external systems and dependencies. Beyond the scalability improvements, this also means you can containerize your application. There's nothing that you need to like orchestrate across different teams in your company in order to make your application work. And of course, elasticity works in that case as well. Just start more or fewer instances as you see fit. I actually have a demo to show that, but since it's just a 20 minutes talk, I can't do that. So the last thing I want to mention here is what we call interactive queries. So what we allow you to do is, if your application does some stateful work, like the red database icon in here, we allow you to directly expose that information, the latest processing result of your application, to other applications. For word count, this could be like, what is the latest count of the word hello? This gives you a lot of flexibility because you can now use 2 different approaches and you can combine the 2 approaches as well. If you need to exchange data between your application or microservice with another application or microservice, you can either do this indirectly through Kafka as the communication channel for all this information, or you can expose it directly to this other application. And you can also mix and combine these 2 approaches as you see fit. For some use cases, it makes sense to decouple. For some, it makes sense to couple. And for some, it makes sense to couple at the beginning, but decouple later on. And just to highlight here, like these other applications when you use interactive queries, that doesn't need to be a Java or Scala application. That can be like any programming language that you want. It could be JavaScript, Python, even PHP if you're into that, or COBOL. And do you remember this earlier example that I showed with this roadmap, the continuously updated dashboard? The thing that allowed us to get rid of the database in this use case is this interactive queries feature. Because you no longer need to have a database just as a handover point between your stream processing part and the serving part. Might be the user-facing serving part. And you can expose this, for example, through a REST API. You can use Thrift for that. You can use a custom in-house protocol that you have. Whatever you favor, you can implement that. So here, this is an example of a REST API that we built for a demo that we called Kafka Music, where we're generating charts in real time based on incoming events, which song has been played by which user, and you can query that live through a REST API. And of course, to sum this up, security is supported as well. So if you want to encrypt your data in transit when you're talking from your application to your Kafka cluster, want to authenticate or authorize your application, so only some of your applications may get the sensitive data in your cluster, that is supported as well. So to wrap this up, as application developers, we really want to build applications and not infrastructure, because this is too complex, too time-consuming, and too painful. And with Kafka Streams, what we wanted to do in the Apache Kafka community is give you a tool to build these cool applications that power your core business without having to shoot yourself in the foot. And if you want to learn more about this, I give another talk at a Kafka meetup later today, so you can drop by if you have the time. And you can also grab me at our booth. We have one in the main conference area where I have time for questions more than I might have here now. Thank you.